In this video, we are going to talk about EMC. It's a very popular topic and it can help you a lot because what we are going to talk about are some measurements or how to do measurements directly in your lab. So maybe you can find out if there is problem on your board before going to EMC measurements, or if you had some problems during EMC measurements. uh, what we are going to talk about is to show you how you can do some kind of verification after you fix your board, how to verify it in your lab. Is this what we are going to talk about, Ignacio?
Yes, indeed. That's what we're going to talk about.
And I would like to point out uh, we are going to talk about some kind of cost-effective or accessible solution for everyone, ideally not using super expensive measurements and probes. So yeah, I'm going to ask Ignacio, what do you have? What you are going to show us today?
Well, what I have today. So thank you. Well, first of all, thank you, Robert, for having me here. It's a pleasure. So today the goal is to talk about near field probes and about some techniques to identify noise sources and to troubleshoot PCB designs or any kind of noise source before going to the lab, or as you said, after coming to the bug with a failure or with some emissions. And the main goal is to enable hardware designers and EMC people or any kind of manufacturer to be one step farther or one step closer to make EMC easy and fun.
Okay, and you are going to do some measurement, for example, on these power supplies. They are like
Mhm.
same three power supplies or similar power supplies,
Yes.
and we will use, as you said, near field probes. So I think
Mhm.
we should start with something like, what is this near field probe? Because I understand it's not like exactly same measurement as what they do in EMC lab, correct?
Indeed, yeah, that's correct. So in the EMC lab, in an EMC lab, what you have is an anechoic chamber, and they place an antenna, normally at least 3 meter far from the device. So from that moment, we're already talking about far field measurements. Here, what we measure is near field. So these two are related, and and they are measured in different ways. And the good thing is that you don't need an EMC chamber to start troubleshooting your system, and this is what we want to do today, to use some small, cheap, and easy to use devices to detect and solve and attenuate noise sources.
Uh, okay, so basically with these near probe measurements, we still can find out if there may be possible problem, and we can also
Mm.
may find out if we fix something, it will disappear. That's how these near field measurements can help us, correct?
Yes, that's correct.
Okay.
So yep, they are very good giving you relative measurements. So they are very good to show if when you make a change in a design, that change has an impact. So EMC has a lot of trial and error, and the problem is that normally you have very long cycles. So you make a change, you need to wait to have a slot availability in the EMC lab that can be in days or even weeks. And then you go again to measure. So with near field probes, what you can do is really reduce that time. Um, they don't give you perfect measurements. They are not made to give you super accurate measurements. And but this is something that you don't need. For that, you go to the lab. These these probes are very good to see if something that you change in your design is going to have an impact in the chamber, in
Hmm.
the real
This is
measurement.
good to point out. Yeah. So what are these near field probes? I can see them, some of them like the blue stuff there are.
Yes. So here we have some of them. And one thing that we are going to see today is that there are a lot of them, but in the end, you can class, so you can narrow it down to two probes, so to two types of probes. So let me bring some of them here out of the box.
Do we need to buy them, or I think you mentioned you have some open source probes, so basically people
Yes,
can order PCBs?
that's indeed a good question. So there are two options. You can buy them, or also you can even build them. And this is something that I have been working on this year, which is on building an open source project on the field probes. So I want to make it very accessible. And now what I'm very happy is that I received the probes, I validated them, and they are working, and they can be found on the internet, and all the files, everything can be found online. And what I'm doing right now is writing a test report or a test plan and of the results, and I will also upload it here so that in the end everybody can have
And
access
today
to
we
it.
will compare them with the probes which you bought.
Yes, so indeed, what we have here is the different, let's say, PCB probes. So some of them are those from the open source project. So let me see if you can see them here. Some from the open source project, some of them are from other manufacturers. Here are the ones from the open source. I have some of them already with the connector assembled. Those are the ones that we will use today. Let me find it here. And so this with a loop, with a circle, and then this is a magnetic probe, and then also we have another kind of probe, which is the electric one that has just a long trace. So those are PCBs, and we will compare them with some commercial ones. So those are from TechBox. You can buy a kit, and then you get four types of probes. So in this case, they send you three magnetic ones, and then also one electric. And so today, yeah, we will compare if it makes sense to build your own probes, if it makes sense to buy a new kit of probe, and why. So what do you need to do, or what is the best approach? And for that, so you always need to remember, why do you need a kit of probes?
Okay, I think maybe we should do some measurement, and then we will continue explaining also the setup and everything else. So
Perfect.
let's measure something.
Okay. So here what we have is, so we have an oscilloscope, and for now it's completely open. There's nothing here. And at the same time, we have a bunch of probes, but what we want to measure is really simple. So we have the signal generator, we have one cable connected to 50 ohm, and then one cable coming back to the return. And then, so what we want to do is to check, okay, we know what, so we want to compare what a near field probe can measure versus what we are injecting. And the good thing of this simple experiment is that with a signal generator, you really know what you are injecting. So you have a signal, you have a sinusoidal signal, you can inject a square signal. So you really know what's happening there. And what is very surprising most of the time is that the probes, some don't measure what do we expect that they measure. And this is something that we're going to see right now.
And you say that you are using oscilloscope, yeah, but you are using a spectrum analyzer feature or function of standard oscilloscope.
For now, it's going to be just time domain,
Okay.
and there is a reason for that. Is because in frequency, so we are very used to see the signals in frequency, and we tend to forget the time aspect of the signals. And I think that it's important first, before moving to the frequency domain, to stay a little bit on the time domain to understand how probes work. And this is what we are trying to do today. So here, so the signal is 20 kilohertz, so we are going to stay in, we're going to go to higher frequencies. So you know that the normally radiated frequencies so are more or less in the megahertz frequency. So we are going to inject a signal. Let's start, for example, with 2 mega. So this is what we have right now. And at the same time, we're going to measure just the channel 1. We're going to disable everything, and we're going to see what we see here. So let's start. So we need a little bit more of a scale because otherwise we're not going to see a lot of things. So here we start to see some changes. It's very subtle, so but already we see that we have some measurements.
So what kind of probe are you using?
So here, I am using a magnetic probe.
So this with the circle, these are magnetic probes.
Yes.
So what's the difference between magnetic probe and electric probe?
That's a good question. So we have talked before about near field and far field. So what happens in these two situations is that in far field, you don't really know what is the main field. So you know that the wave impedance is constant. So there is no difference, let's say, between electric and magnetic field. But when it comes to near field, you have a predominant character. You have a predominant wave. Either you have magnetic field or you have electric field. And these two, a near field area, they can be very strong. So what do we when we want to detect specific sources of noise, we are looking for specific types of signals. So that means that we really need to be specific, or we need to be selective on the kind of signal we are looking for. And the first step is to start differentiating between magnetic signals, magnetic fields, and electric fields.
So basically, if someone doesn't know, they can start with one first, make the measurements, and then also start the other one and make the measurements.
So the best approach is to start with one of them, no matter which one, a big one. So why there are two different, or why the circle is different, is because of the sensitivity. So bigger the probe, be higher the sensitivity. And that means that you can start to capturing signals from broad areas. And it's a good step for starting to really to answer, okay, if there is some noise in this area or not. And then later you go for smaller probes that can help you narrow down the
specific
area.
Component or specific area. Mm-hmm.
Yeah, that's it.
Okay, so how do we make this measurement?
So in this case, so there are two things that are important. First is the type of probe you use, and also where do you place them. So magnetic fields have not only magnitude but also orientation. So that means that depends a lot on how do you place the probe that you are going to measure in one way or the other. And this is also something that you need to consider that can be against you, but it's something that you can really use in your favor, because in this way you can know where the noise is coming. Or so here we already see that we are measuring, and for example, if we place the probe directly over the cable, we are measuring. But if we turn if we start rotating the probe, the signal is different.
Mm-hmm.
And so you need to play with these three factors. It's first the type of probe, the size of probe, and the orientation. So let me
So what do
amplify
we measure?
here.
I'm curious.
Yes, so I'm going to also increase the amplitude so that we can see.
So also your
Unfortunately,
neighbors can see it.
yes, of course. Okay, now I think that we are talking a little bit. Okay, so what I have done is to increase the amplitude, but not the frequency. I have not changed the frequency or the waveform. So what are we measuring? So this is already quite good. So it's current, right? That we were injecting a sinusoidal signal. So we are seeing a sinusoidal signal, which is already okay, great.
What is the frequency of the signal?
That's what we are going to measure right now. Let me add some cursor here. So here we see that the frequency is 2 mega. So it's very current with the frequency that we have injected. So
So it's
basically
same,
what
yeah. We are using.
it's
Oh yeah, okay.
yeah, it's exactly the same. So what we are measuring is exactly the same signal, but with a well, not exactly. It's not really true because if you see the amplitude, so I have injected 10-volt peak peak, and here I am measuring more or less 40, 20, 40, let's say 50 millivolts. So the amplitude is completely different. So it's much more attenuated. And this is because of the probe. So the probe has a ratio. So it's normally not 1 to 1. So in the end, a near field probe, a magnetic probe, is a transformer. So what we are doing is injecting a signal that is coupled, um, so that generates a magnetic field, and then we capture that magnetic field. But in between, so we have a part of the signal,
Mm-hmm.
and this has the inconvenience of that we are losing amplitude. At the same time, it helps us a lot to, for example, not destroy your oscilloscope or spectrum analyzer, because here I am measuring a 10-volt signal from a signal generator. But imagine that you are working in a EV charger, for example, or something like this. So something with high voltage. So it's very convenient to have this signal attenuated.
Mm-hmm.
Okay, let's do another experiment. So here, so we have seen that if we inject a sinusoidal signal, it's exactly the same or similar.
I'm curious. I'm curious.
Yeah,
Before we go to next measurement,
yes.
can you twist the cable? I'm just curious.
Sorry.
Can you twist the cable? I'm just curious if it will change results.
Yes. So here, let's do it. Okay, I am measuring on the positive.
Yeah.
Then I am seeing this. I am measuring on the negative. I am seeing this. So what happens? So Robert is asking what happens if I twist cables. It seems that you hear somewhere that twisting cables is beneficial for EMC. Let's see what
I
happens
don't know
here.
if it's benefit. I would like to know. I don't know.
I don't know. Never measured. I never measured the near field of a twisted cable. So let's see. So let's see what I'm measuring here.
Ah,
Okay, something is
no,
there.
no change.
So okay, it's not perfect, but if you remember, before we were having more or less 50 millivolts of amplitude. Here it has been a little bit reduced, but still, we see that it's not a magic bullet, right? So it's something there. What happens if I go back?
Yeah, it's
If I,
bigger. Mm-hmm. Mm-hmm.
so you see, so there is difference. There is a difference. You are attenuating, and you know why that happens?
Because they are canceling each other or something. I don't know.
Yes, so that's exactly the case. So they are canceling the problem in so in a in a book this should be so you should be able to measure zero or so in theory the field should be canceled enough. What happens is that in reality the twisting is never perfect, and that's why so you need to be very careful on how you twist and the distances and the installation, but it has didn't reduce so the amount of field, so it's always a good technique. Still you always need to see if really makes sense to twist all your cables or it's going to bring you more pain.
Okay, let's do the next measurement. Okay, I interrupted
Yes.
you.
No, not at all. That's a very interesting experiment. Right. So what we can measure? So here we have okay a sinusoidal signal. This is so the double is because of the trigger and the oscilloscope. So here we see the signal exact frequency exact. So all everything quite similar. What happens? So here it's a very controlled experiment. So we have a perfect sinusoidal waveform. In reality, when we are switching a power supply, when we are switching a converter, we normally have so square signals or trapezoidal signals. And that's why I think that it's very interesting to know or to see what happens when we inject, for example, a square signals. So what happens if here, so now I change to square signals. Oh, 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 life is not as beautiful as you want. So same frequency, same amplitude, completely different
Oh, like
measurement,
much worse, much worse.
much worse. And that's why. So the perfect square signal is the worst nightmare for EMC. So here already we are seeing something that is completely different. And at the same time, it's not a square signal at all. So what is happening here?
It's mostly happening at the edges, so that when the fields are changing,
Mhm.
this is exactly what I would expect. Yeah,
So we know
frequency
that
should be similar now,
we have injected 2 megahertz signal. So you think that we should have 2 megahertz
but
somewhere?
between two of them, yeah, like this.
Yes. So more or less. So yeah, here we have. So we want to be more precise. If we move them here, so here we have 2 megahertz,
Mm-hmm.
and so this comes from a square signal. So we have this so this rise, and then we have down, and then rise again. So what do you think that we are seeing here?
What the rest of the signal or what? Maybe some reflections or something. I don't know.
Yeah. So in here we know that we are getting something related to the original signal, but it's not the pure signal. And at the same time, what happened? Because when we injected a sinusoidal signal, we were really seeing the same signal. Then the question is, we were really seeing the same signal, or it was the related signal from the original one? Um, and so here, what we are seeing is the derivative or the derivation of the signal. So and it happens with square signals, but also with sinusoidal signals. if we compare the initial signal with the one that we were measuring, we would have seen that this shifted. And this is where near field probes can be tricky, is because sometimes we are so obsessed with looking for the exact signal that we think that we should measure, that we in the end we get crazy and we don't find what we think that
this is very, very important.
And so here we have the 2 mega, but also we are seeing that we have different so we have different amplitudes for different frequencies.
And if you use the other probe, how is it going to look?
So let's see. So you will use
electrical one.
Yep. Let's go for it. Let's see what happens. Take. So here I have the eProf. So I hope that is working. It has different sensitivity, I think. Okay. Yes. So here, so we see something, but it's completely different from here. But this one has a very, very low sensitivity. So I need to here a little bit of amplitude. This looks like a square signal. Maybe not perfect, maybe not the one that we are dreaming about, but this is something that reminds us to a square signal.
Again, you have to rotate it and try in different places.
Yes. So here is the same. Yes. So different way of working, but also same way of working with them. So it's the type of probe, the size, and the orientation. So this, for example, this is something that I think that I will rework on the next iteration of the open source project, because this has very, very low sensitivity. So it's really to point the very specific, very small sources of noise. So for example, if we take one
commercial one, I would like to see the expensive one.
The expensive ones, you think? Okay, give me 1 second that I bring the specific coax cable for this. Here. So let's answer the question. Does it make sense to buy a fancy set of probes? Great. So we have a commercial one. So these I bought them directly from a manufacturer. And so the main difference, and what I like is, so it's the mechanics. So it's that it has a plastic handle, and that, by the way, that's one thing that you need to be careful when you use near field probes, is that they are not isolated. So it can be dangerous to use them directly with high voltage and higher than 60 volt, and voltage levels that can be dangerous for us. So always be careful when touching and when moving close to high voltage.
Can you also influence the signal if you touch it, for example, where the signal is or something?
Yeah. So the challenge with these ones is that it's very easy to touch here and to interfere, or even to place the hands over it and then and then touch it. So you need to be aware of what is your influence.
Mm-hmm.
And this is one of the advantages of having one of those.
Mm-hmm. Okay, so have sensitivities.
So let's see what we can measure here. Okay. I mean, we have more sensitivity, but not much more. So not a lot. So
Yeah, it is a little bit better, but
yep. Then I think that we are way close. So let's see. Also, we will measure later in the board, and because it's true that so what we are doing here is so we are injecting a signal on a cable, and it's an alternating a signal that is switching. And at this moment, I think that what we measure, the main field that we measure is more magnetic, and that's why also in this case we're not measuring a lot. And so one thing that we can see is that for now, and apart from the plastic handle, there's not a huge difference between having your own kit of probes and the and one that you buy commercially.
Okay, let's do PCB. Or do you have something else with the cable?
No, not really.
Okay, let's do
So
PCB.
we
I'm
can move to
curious.
PCB, and one thing that we can use is a preamplifier, but I think that it makes sense to move directly to the PCB, and also to move to the spectrum analyzer.
Okay, so let's do this.
So what we have is three identical modules in terms of functionality. So it's DC in, DC out, DC in, out, and the three the same. And what we have is, so the first two are based in the LM2735. One version is the Y and one version is the X. And these are the two that we are going to compare. And so the idea of this board was to design the DC-DC converter in all its range, so to ensure that it could deliver all the power and that it could deliver all the current, no matter the load, and also to design the components. So I was evaluating different inductors, different diodes, and that's why this board was very handy to design the new version. And today we are going to use it to see what happens in the frequency domain and what we can measure when we say, okay, DC-DC converters, I have a lot of noise. Okay, what does that mean? What's the impact? And then we're going to measure with different devices. So electronic load. So to add some load to the converters.
What kind of load you are going to enable?
So this is a DC load that we connect directly at the output. And the good thing is that we can increase and decrease it. And in this way, we can see what is the impact on the switching.
Mm-hmm. What is the input voltage and output current?
So this is what we are going to see now. So let me check. So to be sure that I don't blow anything up, basically. So this is the schematic of the board. And as you see, the topology is exactly the same. What changes is the inductor and the diode. I think that in the end it was almost the same. And yeah, so what changes are a few components, but the idea was to see if it makes sense to use one or the other. And what is really interesting for us today is that if you go to the datasheet, is that so these components, these switching converters, so they generate a switching frequency, a switching signal, and they have completely different frequencies. So one is working in 1.6 mega, and the other one is working in 500K. So people tend to use the highest frequency always, which is great for efficiency, or it's great for space. But today we can see, or we will see what is the real impact. So that is not only efficiency, but what kind of energy we radiate when using higher frequencies. So to ensure, so for example, we can see LM confirm the input voltages. So this is the datasheet, same topology. And so the input, we work, this was for a power battery application. So the maximum voltage is 7 volts. So normally we work with
recommended 5. Okay.
5, max 5. So,
mm-hmm.
so this was for a battery of 3.7. So that can be a good starting point. So yes, perfect. So we have here, so the
oops,
sorry. Yes. So we have here a power supply, so it's for 3.5. Let's see, so 3.5 as an input, and current, we will just not limit it. And later we can see also the impact. And we have a spectrum analyzer that we are going to connect as, so to use as a spectrum analyzer, not as a DNA. And what we can is measure everything that comes from the outside.
I'm curious.
Yeah. Yes. So we can connect an near field probe, we can connect a filter with a least. So we are going to measure different parts. So until now, we have been measuring with the oscilloscope the time domain, and with the spectrum analyzer, what we will do is to measure with the frequency domain. So what we have seen is that the converter works. So these two versions, they work in 500 and 1.6 mega. So we're going to stay more or less in that frequency range. So let's say that from 100, so let's start with the minimum, 0 hertz, let's say, until, I don't know, let's say, imagine 10 mega.
I would like to explain for everyone who is not very familiar with time domain and frequency domain.
Sure.
It means when we say time domain, we basically see how the amplitude of the signal is changing in time. And frequency domain, it means we will see all the kind of frequencies which are included in the signal together with the amplitude.
Yep, indeed.
Because each signal can have actually multiple frequencies, and when we are looking in time domain, in the time, it's hard to say what kind of frequencies are included in the signal.
Yeah, and that's why taking a signal from both worlds is always convenient. And time domain is sometimes very hard to identify the noise sources because you see all together. Perfect. So then let's measure. So what we have here is, so to explain the setup we have, and for people wondering why that device in between. So this is a line impedance stabilization network. And it's a device that is very common used on EMC. And for this experiment, it's doing nothing. So it's just transferring the power from the input to output. Later, we will see how we can use it. But for now, it's just transferring the power. So we are going to power the board. So we are transferring the 3.5 volts to the board. And then the first converter is connected to the electronic load. And I think that you cannot see the electronic loads. Okay, perfect. See now the numbers at least.
I can't really see the numbers, but
okay, let's.
Maybe on the other camera it will be visible.
See, yes, here we can see.
Okay, perfect.
So we have 3.5. For now, the output is 0. So, and what we are going to do is to connect here to the radio frequency input port of the spectrum analyzer. Let's start with a near field probe. So whatever we want, whichever we want. Let's start. So we have electric, we have magnetic, and so it's a switching converter. So that means that we are going to have an inductor that is going to take, so to switch and to store the magnetic energy. So one idea is maybe that we start with a magnetic probe. But again, it's always useful to start with those two and see what do you get from there. Great. So perfect. So now we have 3.5 at the input, and at the output, I am measuring already 5 volts, but zero load. So let's see what if we can measure something. So I'm going to take the chance to make some zoom so that we can see very close what's happening here. Perfect. So if we measure, so we are working with the first converter. So it's zero load. So if you ask somebody, hey, is this circuit doing something? They will tell you no, but it's there is no load. Okay, but then now something is happening. So already we see that we are measuring things. So if we change the orientation, so the first thing we do is that we approach the probe to the board. So we start here. This states that the question we want to answer is this board generating any kind of radiation? So then we take the one, not necessarily not a specific one, just one, and then we move it very close, and we see if something changes. So here, what I see is that if I place it very close to the cables, I am measuring nothing. So nothing is really changing, not at the input, not at the output. But when I place it very close to the circuit, then the amplitude, the signal is changing. So already you can answer the question is that okay, this board or this circuit is generating some noise or some energy. It's generating some energy. The next question is, I am able to identify something there because we know that so there is some energy there, but it's true that it's not giving us a lot of information. So we just see a curve moving. So one thing that we can do is, so here we see that the frequency goes from 0 to 10 mega, and that the frequency is 120 kilos. So one option can be is to reduce the bandwidth of the measurement. So as the spectrum analyzer, what it does is that it uses a filter, in this case, so 1 kilohertz, and then makes a measurement, then another one. So if that bandwidth is very big, it's capturing everything that it's under that bandwidth. So it's good to know if there is something, but it's hard to see what specifically it is. And if you reduce the bandwidth, then you can start identifying some areas. So here we see that okay, there are some peaks. Now the next question is, are those peaks coming from a specific piece of information or not at all? So let me add some markers.
If you increase the load, is it going to increase a little bit so it's better visible? I'm just curious.
So let's try it. So for example, so let's first see the datasheet, how far we can go. So here we see that the limits, so it's okay, 3 amps more or less. Yeah, so let's think that we can start, for example, with half and see what happens.
Oh, that's very
Oh yeah.
different.
Oh yeah. Oh yes. So to answer your question, yes, if you increase the load, it changes. And what happens if we increase it even more? So now we are even at double, double, double charge or double load. So we are at 1 amp. Here we go to zero or zero, yeah, almost zero. 0.1, 0.2. So this is also something interesting is that we see that there are changes, but not necessarily in amplitude.
hmm The biggest change was between like zero load and some kind of low load, and then it looks like
Yep.
it's similar.
Mhm. Yes, yeah, indeed. And one thing that is very interesting is to see how far it goes. So here we have started from 0 to 10.
Yeah.
In reality, conducted emissions, for example, the conducted emissions test starts in 150 kilohertz and goes up to 30 mega. So let's see what happened there. So here we have 1 amp. Now we are at zero. So what we see is that at zero in low frequency, it seems that there is some energy. And then when we increase, for example, here 200 milliamps, so the whole bandwidth starts to be PC.
Okay, so what do we know from this?
So what do we know or what we can know? So it's first that we are measuring it with a magnetic probe. So already we know that it seems to be some kind of magnetic energy going there. And second, that we have a lot of frequencies. So we are seeing peaks that go from 0 to 30 mega and even higher. So let's see if we can measure the frequency to see
Okay.
if we see where the peaks come from. So for example, so the first peak and the highest is in 500, almost 20 kilohertz. And here, so we see that we started with the Y version,
Mm-hmm.
and then let's see
That's the
if it's
500 kilo one, I think. Yeah.
so. So here is 520, and here we're measuring that the highest peak is 520 kilohertz. So we are already seeing some coherence between the switching frequency and the emissions we are measuring. What happens if we measure, for example, so the next? So here we see is 1.03 mega. So it's harmonic. So the and this is one of the main challenges of EMC is that you need to look not only for the main frequency, is you need to look for the main frequency and all its brothers, that all the harmonics. And they can go really, really far.
Mm-hmm.
So
So basically, this means if this means basically if it's only kind of one frequency, it doesn't mean there is only one frequency. There will be peaks on all the other frequencies which are a multiplier of the first frequency.
yep, indeed, indeed.
Just the first frequency is the biggest one, tallest one.
So it can be the biggest one, but you can have harmonics going several mega
But
and
it can be also,
several.
doesn't have to be maybe because if there is some kind of resonance or something, then it can.
Yeah, yeah, and indeed, and that's my feeling. That's what we are seeing there. So so here, so we see all that animation from all the harmonics that can go even so up to 100 or 80 mega, and then later we have another. like I don't know, like a little mountain, and that's a resonance. Most probably is because of the near field probe. So one thing that is important is that near field probes don't have infinite bandwidth, and then that at some point they start showing a resonant behavior.
Mm-hmm. That's also good to know. Okay, so where exactly are you holding the probe? Is it about the inductor or?
Yes. So let me move it here. Let me see if you see it from there. So yes. So it's exactly over the inductor. So um, at the center of the probe you have the inductor. And so let me go back to the smaller or shorter frequency. Stop. Let's just start with 50 mega so that we can see the changes much faster. So here exact is really at the inductor.
Okay, if you move it a little bit away, what will happen?
So if I move it a little bit up, so I am here, for example, like on the some capacitors or even over the IC, this is what we measure.
Mm-hmm.
And for example, if I place the probe in perpendicular over the inductor, this is what I measure.
Mm-hmm.
So almost nothing. And that's why it's very important to change the orientation of the probes when you are using them.
Mm-hmm. Okay, so let's change the probe. Will we see something?
Let's see. See. So if we use an electric and E-field probe, let's start. Let's see what we measure, because we talk a lot about magnetic energy, but the pure electric field, what's to hit? So I am using now this one, and I am pointing it directly to different areas of the board. So I am here close to the inductor. Here seems that we're not measuring a lot of things. So the electric field looks to be very silent here. Normally is when you are close to capacitors.
Do you need to change resolution or?
Yeah, let's see if, for example, let's add some amplification to see if there is a difference. Mm, small, very, very small. Okay. Okay, now we start seeing some. Let's see if I can reduce a little bit the
But maybe
television.
do you have load there now?
Yes, we have load.
Okay.
Okay. So so the electric field is lower. Also, the probe is very, very, very small, but we can change the probes. But also, what we can see is that there is some relationship. So, like the waveform is not completely different. The Here I am placing the probe directly on the top of the inductor. So we are seeing that it's capturing also some magnetic field. The difference, let me see, let me make this measurement. The difference, for example, is that here I am on the capacitors and I am measuring things, while before I was not measuring any kind of variation on the capacitors. Um, so the main difference also is that since this probe is much more selective, I am able to measure at component level. So I am measuring at the path of a capacitor, and I am measuring what's happening there.
So where exactly it is measuring? If you have a closer look at the probe, maybe in your presentation.
Yes. So you see here. So I am using this probe, and you see that there is a small,
Mm-hmm.
like a small piece of trace there. So I am placing this trace. Now at this moment that we are measuring, we are detecting some peaks or some values. Let me show you the layout. So I have exactly here. So the probe is exactly at this
Where
this
the
point.
diode is.
Yeah, yeah, yeah. This diode. If I move here to this capacitor, this is what I am measuring right now. Yes. And for
And if you
example,
change the orientation,
so here, if I change the orientation, for example, so if I stay on the diode on P4,
mm-hmm,
here is completely parallel to
mm-hmm,
the board. I am measuring something, but more, not really a lot. If I move it, then not that much. Now I rotated it 90 degrees so that it's now is facing this component. It's really vertical and on this place.
so you really have to play around.
Yes. So it takes a little bit of patience. Also depends a lot on the on what how are you doing it. So because sometimes you go to the lab, you go to the EMC lab, you have a failure, imagine, in 1.6 mega. So you know that your only task is to look for a 1.6
Mm-hmm,
mega. And then you do everything to look for that frequency. When you start from scratch, it's more difficult because you don't know what you're looking for.
mm-hmm. Okay, so let's change to different power supply. Is there something else?
Mhm. So let's see.
Oh, that's the different frequency.
Yes. So let me change here connectors. So yeah, so now we're going to test this one. It's the version X, which was which frequency it had. So this one
1.2? I don't know.
here. So the
1.6.
X, so it's 1.6, which already is quite higher frequency. So in comparison to 500 kilo. So let's see what we have. We have the same input power. So it's 3.5. Here at the output, I am measuring 5 volts. So the circuit is working. And let's start with half amp. Half amp, a little bit less even. And let's see what we have. So the output load is very low. Also because this design has been dimensioned differently, but at the input so we can see already that the DC load, so that there is some switching signals. So this one we have said that is working at 1.6 mega. Let's see if we can find those 1.6. Let's start as we have done before with the magnetic.
Mm-hmm. And so, with the magnetic probe, how do you identify the middle, the strongest point of the probe? Is it in the middle of the circle or?
Hmm. Mm, yes. Let me, but no, let me show you here. Or even, yeah. So here, so you see the magnetic probe,
Yes.
and so the magnetic probe is built in the way that it has. So all this is covered by ground plane.
Mm-hmm. Oh,
So
okay.
so this is to attenuate or so to shield. Sorry, and then there is a small aperture. So it's
Oh,
really
okay.
as a small aperture there. So that aperture is the one you use to peak the field.
Mm-hmm. Okay.
And yeah, but I think that I get what you were asking is that when we use probes like this, for example, that so where is the best place to use cables or to place the cables? So we always need to place them in the center, so
Mm-hmm.
to avoid so to have symmetric measurements. And here with the near field probes, the best is to put it as close as possible. And this can be, so this is small area, this is what will determine the sensitivity. And then that's where you want to place the signal you want to measure. So let's see if here, okay, already I get close and I am measuring quite a bit of things. Okay.
Maybe you need to go back to same scale what we had before.
Yes. So same scale, preamp off, and this was to 30 dBs if I'm not wrong. See. And before also we were measuring, so we're measuring at 200 mega, for example. So let's see if here the signals go even farther. So already we are seeing something similar as before, that we see that it's not only one frequency, it is also a lot of them. And even so it goes until 200 mega, but even so it can go even farther.
But the peak is now a little bit further, yeah.
So now let's look for the peak. So here, so we have one peak at 10 mega. Why not? And so we have, okay, so
again
we
you
have
are holding the probe about the inductor, yeah?
Yes, exactly the same. So here, so we have some peaks, but it's true that in this case, so we are not seeing that the maximum is
1.6
fundamental frequency. So we see some variation. Still, the 1.6, let me look for it so it's easy to see it. Okay, so now, okay. So let's see what happens if we remove all the loads. Oh. So zero load, we are really measuring zero. If I remove it, okay, there is a little bit, but nothing really that we can notice. And if we increase the load, here we have really low, very low load, is 20 milliamps. And then if we increase the load much more, we don't see a huge difference. What we see is a change of the form.
So where is 1.6?
So where is our 1.6, right? Where is it? So let's look for the 1.6. So the 1.6 is somewhere here. You know, it's so 1.48 is the first signal that we are measuring. So
can you point finger, because I don't know where it is, which one it is.
Sorry. So true, because so here that's the very first peak. So it's 1.48 mega. Let me see so that this camera is recording too. Okay.
I think I read somewhere they have to limit the recording time on cameras because they are not like recorders, they are just like picture cameras, and that's the reason why they do that.
I was reading about that yesterday, because I said, why I don't think that it's because of the electronics, or I don't want to believe that. And that was one of the reasons indeed that it's limited to half 29 minutes 55, 59 seconds, because after that they are considered video recorders.
Yeah.
And I was like, okay, thank you for the hint. I will consider it. Me have the so that we have some light. Yes.
Okay, so this is basically a good demonstration that it's not always so easy. So there is a lot of noise. We know there should be noise at 1.6, the biggest one, but
But
no.
where is but where is it? But where is it? Right? What happens? So here, I mean, imagine that without knowing the details, because it's true that, so it has been a long time that I don't remember the details of this design. But normally, so if I find these issues, so if I know that in the data sheet, I should expect 1.6 and I am measuring not, first, it's not the highest peak. And second, I'm not finding 1.6 anywhere. So what I will do is, first, I will take the oscilloscope and measure really to see if the converter is really switching at 1.6 or not, and then measure the switching frequency. So because from there, what I can do is to correlate these measurements with the actual switching frequency, and from there I can extrapolate more data in the lab, in the EMC lab or here, because if I realize or if I see that, okay, the switching frequency is not 1.6 but 1.48, that this is what I'm measuring here, that's okay, because then that means that I can keep working based on that. But it can be confusing. It can be and frustrating.
Okay, so now what? The voltage or the
So
electrical
yeah,
probe?
let's say, yeah, I think that what we can do is see if using different sizes of probes and types can bring us more light or can bring us different information. So
But what I wanted to say, so this
yeah.
1.6 was a little bit more noisy than the other one.
Yes, indeed,
Mm-hmm.
yes. Mhm. So what happens is, and this I can measure, is that here we can see it. So yeah, it's noisier. It's because of two things. Yes. So when you are looking for noise problems or noise issues, you need to think uh, about two factors. One is the frequency. So what is the main? So it's the switching frequency. And second, what is the rise time and downtime of your signal? Because you see you see that the signals are going. So imagine that I am 200 mega, and imagine that here I at 500 mega. So it's going to take some time, but we will see that there are a lot of signals there. So you can have the same signal frequency, but if the rise time is very fast, very fast, the bandwidth the signal that will occupy will be much higher.
That's exactly what
So
is seen between sinus and square
yeah,
measurement.
yeah, indeed. And so in the sinus, you have one fundamental frequency. So that's just one peak. And in the square signals, so you have the rise time, and so you have a signal that is switching. That in the end, if you move it to the frequency domain, a square signal is the addition of many sinusoidal signals, and this is what we see with these measurements. So we are seeing the fundamental frequency, the second, third, all the harmonics, and this is why on EMC, in the end, so the main priority or one priority is to reduce frequency, but the real factor that makes an impact on EMC is the rise time and the load time.
Because if it's faster, then also the edge has to be faster.
Not necessarily.
But
So
for example, even for standard signals like digital signals, if you would like
yeah,
to have faster communication, you would like to use
yes.
faster signal, then edges they need to be a little bit
So
sharper.
of course, and today the ICs that we have and the drivers, they are super fast. And but the problem we find today is that since we have fast technology, everybody uses fast technology. And then you see systems, for example, you see devices that use a very, very high frequency to measure temperature, for example.
Mm-hmm.
That is a signal that changes very slow. So you don't need, I'm going to exaggerate, but you don't need a 1 gigabit to measure temperature.
Yeah, exactly. Okay, do you have more measurements for this one, or we wanted to do the electric
So
probe?
we can measure electrical to see if there's any change, but it's going to be quite similar because in the end, so it's to see what are the so what we can see different. We can compare the size if that's important. I think we have talked a little bit about why there are different sizes of probes, for example, and so those those two are clearly near field probes that are different.
Mm-hmm. Okay.
This one, even if it seems an electric probe, is a magnetic probe, but it has a really, really, really small circle. And this one is an electric probe.
Mm-hmm.
And the problem with commercial probes is that they give you a huge catalog, and then you don't know which one you need, and and it's at the beginning it's hard because you don't know what are you going to need. So my recommendation is that you get so one very big like this one more or less big, but it's still small, and then one really small if you are working on dense designs, so in high speed, very dense designs that you need to measure really small components or small pins or so really
But then
small.
the signal is much lower. Yeah.
Yeah, so it's slower, and that's why sometimes you need to add an amplifier either at the spectrum analyzer or an external one. Sometimes you need a small amplifier, so you inject the signal that you measure here, and you measure it 10 dBs higher, so you are amplifying the signal.
But you are amplifying also noise. So
Yes, and as I was reading recently, the problem of using an amplifier is that it makes everything feel important. So it amplifies it amplifies everything, and that can be hard to identify. So it can be hard to identify the real source of the
I'm
signal.
just curious when you have these
Yeah.
probes. Can we just see difference between the big one and the small one, or in
Sure.
same scale?
Mhm. Yes. Let me see. So
You need different cable always.
yeah, let me see if I can freeze the signal so that I can freeze one trace on the other. So normally most of the probes come with an SMA connector, and but these ones come with this connector that I don't know the name exact, but it's different. So you need a different cable.
They don't want to make it compatible.
Yes, that's what I think.
So you
Uh,
have to buy their cables.
yeah, in the end, they want you to be part of their group. So the cable. No, what I have that is very convenient is a box of adapters. So so that here, so you can see that. If I don't move the camera. is that so an adapter like this that you can connect to the spectrum analyzer and then to any kind of device. So and for this frequency band, these adapters are more than good enough, so they are not impacting the signal. So let's see what we see when we use different size of probes. So for example, if we start with a very big one, we have everything connected here. Connected.
I guess we should say something. Oh yeah, something is coming.
Yes. So let me go back to 200 mega so that the measurement is faster. And related to amplitude, so we have everything off and the attenuator. Okay. So what we are seeing here. So we have, for example, so here we see that amplitude goes, so let's say up to 64. Okay. So imagine, and this is
You can make it
important.
bigger because I guess the other one will be smaller.
Yeah, indeed. And scale. So something like this, right?
Okay.
Let's. Yeah. Okay. So this is whoa. Okay. Want to saturate input. Okay. Let's start. Let's wait. So let's wait for the measurement. So we see more or less what is the amplitude we can get. And this is important. So when you compare the output of different probes, that you more or less use the same family, or that at least they follow the same fabrication. And because so if you are comparing the size of the probes, if they have been manufactured differently, so you can be measuring different things. So it's always convenient to measure or to compare using the same family. And that's why also I want to make different versions of this open source project so that we can have a kit of different size.
Mm-hmm.
So here I'm placing the probe directly on the top of the inductor, and what we see, so it's an amplitude, let's say, that can go up to 70 dB microvolt. And we're going to see what happens if we use exactly the same setup, except that we change the size of the probe.
Okay.
Okay, let me clean the measurements so that we're sure that we measure the correct values. Okay, then I place the probe exactly on the top of the inductor or over the inductor. Okay.
It's not much smaller. It
Not
looks
much.
similar.
Yeah. So we're going to see what's the difference, and this we can easily see in the data sheet of the probes. Okay. So here we see so the difference, or the challenge is that, so with this one, so we were covering so all the inductor but it was placed. So it was placed on the top of the inductor. Here it's the same, but we see that so that the surface is limited, so it's covering the inductor. We're saying that we're capturing mostly the same. The difference that is going to be, we're going to see, and we can go back to the previous probe, is that from the moment that I move the probe a little bit, just a little, all the signal, or mostly of the signal disappears. And that's the main difference, is the spatial resolution. So in this case, we were cheating because we know exactly where to look at. But what happens if I move? So now I have the probe a little bit closer, but it's already far, so it's not anymore in the inductor. So the signal almost disappears. So it's capturing very little part of the energy. And what happens if I do exactly the same, but with a bigger probe? So that if I place it at the top, and then I move it, that is not there anymore. So if I start at the inductor, so we capture the initial signal. If I move it, so the first thing I see is that I don't have that much space to move the probe. So I am already colliding with the connectors, with the other ICs. So the spatial resolution of this one is not that much. So I don't have that freedom. So I really need to move much farther to have the same attenuation. And indeed, so in this case, I am really far, but still
and
the
you are still
probe
picking up the inductor.
Yeah, it's still covering part of the signal from the inductor. And what happens is I use really the smallest one.
Okay, I'm curious.
So if I start at the inductor, so I'm going to see if I can get the maximum amplitude. So we don't get us. So I will need to really center it in almost half of millimeter on the inductor to get the same high amplitude. And I see that I am not able to get it. And as soon as I move the probe just a little, so not even
you are
not
losing
even
signal.
It goes away. So we lose almost all the signal. And now I am out of the inductor, but it's still very close, and we capture nothing.
So it's very important to actually start with the big one, because you can very easily miss. You just move it a few millimeters away, and then you will never measure it.
Yeah, definitely. So always start with the biggest probe, and then look for an area, identify it, and start using a smaller one, and one that allows you to move around the system, and so that lets you identify when the signal is there and when the signal is not there anymore.
What about the third power supply? Are we going to measure it?
No, not really, because I think so it's not working that fine. So that it's not giving the good output signal. So I prefer to stay with just the first two to compare the frequencies and so on.
Okay, I think you have one more measurement, yeah?
So we can do that if you want. So we have, and
very quickly, we can do that very quickly.
Okay, as you wish, because so this is the setup to measure conducted emissions with a DC listen. So that we measure it with the spectrum analyzer, and we connect it to the computer.
And basically, we should see something similar to what we've seen with the near field probes.
Yes, so we're going to see something similar. The difference is that this is the official test. So if you are able to measure here conducted emissions, this is what the conducted emissions that you will measure in the EMC lab.
Okay, let's do the first one, because the first one was something what we expected, and just do this very quickly. If someone would like to know more about these measurements, I already done some videos on these measurements.
Yes.
So people can watch these videos. Here I would like to just compare the results and let's see.
Perfect. Let's do that.
And I would like to point out, so this is different kind of measurements. We are not measuring the magnetic field and electric field around the PCB, around the components, but we are measuring noise which is going through the cables, correct?
That's correct.
Or simply to say.
It's completely accurate. This is what we're going to measure. So this is one of the official EMC tests, or one of the tests that we do when we go to the lab, when we want to certify a product. And it's conducted emissions. So what we do is we measure what goes over the power cables. And what I like about this test is that it's very easy to replicate at home, let's say.
But for this test, I think you need to have some kind of metal plate or something, or?
That's correct. You know already the details. Yes, so you need a ground plane. And so in an EMC lab, that ground plane is made of copper. So people use a copper surface. For pre-compliance measurements and for home measurements, you can use aluminum. So this is what I have here.
So it's not visible in the camera, but that's
okay.
aluminum plate?
Yes.
Okay, it's not like standard anti-static mat.
No. So this surface, let me move it here. So this surface is an aluminum textile, let's say, and that it's very comfortable. It's very easy to use and to build. So some pre-compliance measurements. So please don't consider this setup as the final one for the EMC lab. It's just to prove or to show that there are tests that you can easily do at home, and that you can relate the measurements to somehow to what you measure with near field probes.
Maybe you can correct the camera again. Okay, thank you.
See, also we're recording it here. So this should be connected. This is connected here.
And I would like to explain a little bit the black box which you have there. So basically it is, I believe, if I understand right, it's some kind of standard impedance. So all the measurements in all the different labs and everywhere else basically are related to something what is common between the measurements.
Yeah, indeed. So EMC tests should be easy to replicate, or should not be dependent on the conditions you make the test.
For example, power supply.
So power supply. So the power supply I have here does not mean that it's the same that the EMC lab has. Cables. So no matter if you use one kind of cables to power your system. So the idea is to provide a common impedance and in these frequency range for conductive emissions. So yeah.
I learned something from the previous videos.
Definitely. That I mean, you recorded very nice videos about with me about conductive emissions and using these pre-compliance setups, and it's amazing how far we can go with relatively small setups. So what I have here, so it's the software. So I'm using the textbook software to measure. It's connected, so the computer is connected to the spectrum analyzer, and what we have is a frequency range of 150K to 30 mega. So that's the standard frequency band for conducted emissions industrial applications. And here we see two lines. So one is for the average, which is this one, and then the other is for the quasi-peak. So today we don't have time to go there. And so only to know that in EMC tests, we measure two magnitudes. And the main reason is because it's not the same to have a signal of 1 megahertz that is always there, that we're having 1 megahertz that is only sometimes.
Mm-hmm.
So that's why we need these two measurements. So I connect the power supply. I see here 5 volts. I add a load. Let's make it interesting. So let's see. We can so 1 amp can be too much for this power supply. Let's say 800. So 800 milliamps, which is already quite a bit of load. And so on the spectrum analyzer, we see that there are things moving, but we are going to make the measurement here directly because it's not the same. So if I click.
So this software is connected to your spectrum analyzer?
Mm-hmm. And it does the test in the same way that it should be done in the EMC lab.
Oh, I can see the peak there.
So what is and this is one of the reasons why we are using a software. So why we are not just pressing the button here and in the spectrum analyzer and then plotting the result, is because here in this window, so it's showing a window now between 2.5 mega and 5 mega, and then it's making the measurement. So the software, what it does is that it divided the interval of between 150K and 30 mega in smaller windows, and then it makes the
so it's more precise measurement.
So it's more precise, and it's also a requirement from the standard.
Mm-hmm.
Because they require you a minimum amount of points, measurement points for the frequency range.
Oh, so you get even better resolution then.
Yeah, and a spectrum analyzer like this is not able to, so it doesn't have enough data points for the whole
because you could
frequency
skip
range.
maybe some of the frequencies.
Yeah, because if you sample here, there, and it's not enough the sampling, you can easily skip data points.
Mm-hmm.
And that's why we use a software.
So the power supply is really bad. This is what it means.
So yes. So that's a good answer. So if we use this system as it is without any modification, without any kind of filter, so this measurement, what it's telling us is that the noise is over the limit. And you see that there are small markers here. And this is what it's telling us, that we are 37 dBs over the limit, and that we are that we are 7, 4. So we have several frequencies where the system is failing. And what I like of this test at home is that if the test setup is correct, that I believe that there are some parts that we can improve, but we will not get a huge difference. What we are measuring here is very similar from what we can get in the EMC lab, and this is way cheaper to install.
So I understand now. Oh, okay. So basically, this can really help. This very simple setup can really help to kind of measurements, and you can also, I guess, you can also see the fixes. If you fix something, then this frequency will not go out through the cables.
That's the idea. So this setup with the near field pros can really help you to pass conducted emissions first time, and to avoid so many back and forth, travel to the lab, pack everything with you, make the test, come back. So which is time consuming and expensive, because every day in the lab is expensive.
Are these EMC, so, okay, I will formulate the question. So, are these EMC problems going to be always visible also through the cables or not always? Through this conductive measurement, I mean.
So you mean that if we are able to detect the
I mean,
conducted emission?
can you fail EMC but not see it here?
So yes, because so this is just one of the tests. So this is conducted emissions, and here what you measure is the noise on the cables.
That's what I mean, yeah.
What we are not measuring is, for example, radiated emissions. So
So
we don't know.
it doesn't have to be always correlated. You can have EMC, but
Yeah. So there is some at some point there's that correlation between radiated and conducted results. So if you reduce most of your problems of conducted emissions, or you attenuate the noise going over the cables, you will already solve quite a lot of things, or you will reduce a lot the risk of failing radiated emissions. Because one thing that you can do, even if it's not the frequency range of the standard, is increasing the frequency range and see if you will have much high frequency, so higher amplitude in higher frequencies. And even if it's not perfect, you will know. So you will know more about your system, because the idea of pre-compliance test is not to be perfect. So it's not to have the perfect result, the perfect graph, or the perfect number. It's really to reduce risk. So it's really to be more confident when you go to the lab.
And I guess once you go to lab and you have some kind of reference, then it can be very helpful, because then you have the reference, you see
Yeah.
like the official paper. Then when you do these measurements, you can see kind of maybe relative,
Yeah.
but you still see same peaks, just maybe different values.
Yeah, indeed. So what can change sometimes? So it's the amplitude, also because the laboratory has some variations, so they have some variability. So it's normal that you have some changes. That's why it's very recommendable when you are building your setup and when you are doing pre-compliance, that you ensure that you go to the lab with more than 60p of margin. So so that you are sure that even if the laboratory has some variation, it's already you will still pass the test.
Okay. So what are the frequencies? I noticed 500 is the first one, then 1000.
Yeah. So here, so we have 1 mega. We have the biggest, so the highest frequency, which is 500, which also relates. So what we were seeing before, right? So
520 was it, or I don't know. Hey, 520.
520. And so here we see,
And
so
all
okay,
are the
here,
harmonics.
yes, so indeed. And so everything is correlated. So it's the main switching frequency with what we were measuring with the near field probes, with what we are measuring now at the conducted emissions. So and also this will be related to what we will measure in the EMC lab. So if you go from the end to the beginning, that means that with near field probes, you can already start debugging your system and identifying potential sources of problems.
And I would like to point out the graph. It may look like the peaks are going closer and closer, but it is logarithmic scale, so that's why they are getting closer and closer.
Yeah, that's a good point.
Okay, I think we went through everything. Or what do you have in your presentation? What else?
So I think that we went almost through everything. So the idea is here, what are the types of probes?
We didn't want
Little
to
bit of,
scare people with these
yeah,
equations.
a lot of equations, but no problem. This is not an electromagnetic class. No, you can stay calm. And so the fundamentals of near field probes, basically what we are doing is we have PCBs, or we have electronic systems that create or generate an alternating voltage. Alternating voltage creates an alternating electric field. And what we are doing is capture that field to transform it into alternating voltage. And the same with current. So that's the main purpose of these two probes. We want to capture alternating energy. So it's the open source project, and you will be able to find more information. So in the website and also in my website, it's true that I am now doing some housekeeping and all the information. So I'm writing a guide, I'm writing a lot of documentation there. So I really want to make this accessible and that people can measure and can do whatever they want in any corner of the world. So this is the commercial set that we have been using. And so here you have the cable and the preamplifier and the 4 probes. So the 3 magnetics and 1 electric. The very simple setup.
This was the cable.
With the cables. And this is the conducted emission setup that we have been using. Key points, because it's very easy to overlook. So you have the power supply, you have the LISN, so the line impedance stabilization network, and the device under test. So in our case, the device under test is the board with the 3 converters. You need to place the DUT over a non-conductive surface. The standard says that it's 5 centimeters, if I remember well. So it's always a calibrated or a known height. And
distance from the metal plate.
Yeah, and this is to change. So it's to change the capacitance between the setup, also between the DUT and the cables also, and to the ground. And this is a conductive surface. So in compliance environment, this is copper. In real life and in home setups where you need to move your setup, or if you need to visit a customer and you need to support somebody, this roll-up aluminum plane works perfect.
I didn't know something like that exists actually.
Yeah, so it's very useful. It's Techbox doing that, manufacturing that, and it's it's quite big. So it's like 2 meter surface, so you can cover the whole table.
This is what we were doing now.
Yeah. EMC view, so the schematic that we have seen, the board, the frequency, sheet. Yeah.
We have even worse.
Even worse. Yeah, this was the first measurement. So yeah. Oh my God. And yeah, some references about some more information. So I wrote an article this year about this near field probe project, how to design your own near field probes. What is the process that you should follow if you want to build them from scratch? And everything is linked here in the repository. So all the information is linked here. What else? Yeah, interference technology and so on. And also, if I remember well, I added the probe so in Hackaday, so that it's accessible and so the idea is to store here or to share here more results. So here, yeah, exactly same setup.
Perfect. Thank you so much, Ignacio, preparing all this.
Thank you to you, Robert. It was a pleasure.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KeyCut, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.